In the previous video, we talked about or defined vector fields. Now we'll talk about a couple of operations on vector fields. First one being the curl. So say you have this vector function or vector field f, meaning that each of its components is in turn a function of the three coordinate variables, x, y, and z. Curl of f, and here is the notation for it, inverted delta, and it looks like a cross product. That's the easy way to think about it. Well, here's what it actually is. Easy way to think about it is to set up this determinant. Top two rows will always be the same. The bottom row is made up of this P, Q, and R, X, Y, Z component functions. Here's how you take it. Let's say your function is this thing, X, Y, Z, X, Y. Set up your determinant. As I said, the top two rows always stay the same. So this P part, XZ, it goes down here. This is the Q part, YZ, it goes down here. R is XY, it goes down. R. Now what does it mean? You take this determinant. The I component will be, let's see, the partial of this with respect to Y, which will just be X, minus partial of this with respect to Z, which will be Y, minus the J component. J, it'll be this with respect to X, so it's Y, minus this with respect to Z, which will be X. That, when you do the K one, it's going to be 0 minus 0. Here's your vector. By the way, the test for whether a vector field is conservative or not is whether the curl equals 0 or not. Curl's 0, it's conservative, and if it's conservative, the curl's going to equal 0. So this was a case, this vector field here was a case of it not being conservative. And I think I gave that as an example when I was talking about vector fields. Conversely, here was another example I did, and this one was, I believe, generated from a potential function, so it was conservative in that respect. Let's check its curl. P, it goes there. This is Q, it goes there, and the R goes there. Let's see, I component. X minus X. J is going to be Y minus Y. Z will be Z minus Z. All zeros, the zero vector. This is a conservative vector field. Divergence. By the way, the curl operates on a vector and it produces another vector, right? Vector in, vector out. Vector in, vector out. Divergence operates on a vector field. Get a scalar on it. What does it mean? Well, here's the notation for it. Divergence of f, or this looks like a dot product here, because operationally it is kind of a dot product. We'll take the partial of the first component with respect to x plus the partial of the second with respect to y plus the third with respect to z. Here's the divergence. Here's a simple example. Here's our vector field, xz, yz, xy. See, this guy with respect to x will be z. This guy with respect to y will be z. This guy with respect to z will be 0. Add them up, z plus 0 equals 2z. That's the divergence. Divergence is pretty easy to take compared to a curl. So here's an example. Find both the curl and the divergence of this vector field. Set it up in vector notation as opposed to a linear combination of the standard basis. There's your P, there's your Q, there's your R. So Those guys go down here. Remember, the top two rows are the same. So let's see. I component going to be this guy with respect to y, which will be 3e to the minus z, minus this guy with respect to z, which will be yz. I won't do the rest. Partial's okay. There's the curl. Now for the divergence. This guy with respect to x, e to the minus z. Guy with respect to y, 4z squared. Guy with respect to z, minus 3y e to the minus z. And all up, that's the divergence. One last example. A linear velocity at a point in a rotating body is described by this vector. V equals omega cross r, where r is the position vector, and omega is rotational vector, which has these three components, omega 1, 2. Know that this is true. Omega equals half the curl of V. Well, what's the curl of V? Curl of V is this. V was omega cross r. Let's find out what omega cross r is. That is a plane cross product, not a curl. Omega cross r. Omega 2z minus omega 3y. J will be minus there because it's a determinant. Remember how to take determinants. Omega 1z minus omega 3x. Etc. So here's V, or omega cross r. Now then we want the curl of it. Now we're taking the curl of this thing up here. Now that means curl, not a cross product. Two different meanings of that x. This is a cross product. This is a curl. So cross product, or the curl of V. This thing. Here's our P, U. Notice the sign. So it's now omega 3x minus omega 1c. And then r. Take the curl. Let's see. First thing is going to be this with respect to y, which will be omega 1 minus omega 1 plus omega 1. Do the other two components, and you get this, which is 2 omega. And that means we proved what we need to prove. This was the curl of V. Proved what needs to be proved. And that ends calculus, differential vector calculus. The rest of this module will be integral vector calculus. Quick, and for differential vector calculus, we covered three operations: gradient, the curl, and the divergence. We did curl and divergence in this video. The gradient took 3 different videos. For a gradient, what goes into it is a scalar function. What comes out is a vector field. Curl, what goes in is a vector field. What comes out is a vector field. For divergence, what goes in is a vector field. What comes out is a scalar function. Try to at least get the inputs and outputs right. Anyway, the next thing we talk about is integral vector calculus, and starting with work integral.